Okay, so first I would like to thank the organizer for this invitation. It's always a pleasure to come to CIRM and precisely be in front of such an audience. So I will talk about a joint work with Erwan Faou and Miot, and it is about dynamics of almost parallel vortex filament. Mainly the talk will be on the results, but what one has to have in mind is that the proof won't be so difficult. So I won't spend time on the proof. I will more spend time on the statement of the results. Okay, because moreover, as you will see, there are models that aren't studied too much, and there are interesting models in fluid dynamics, mechanics, and there are lots of things to be done at the level of the existing models and also at the level of deriving new models on these topics. Okay, so what is a vortex filament? It happens in fluids, where 3D fluids, where vorticity is very concentrated along a curve. So we are in R3. So we have to see the evolution of a curve in space during time. And of course, as you know and imagine, vortex filaments are an important feature in fluids, and more precisely in turbulent fluids. And in particular, the question of colliding vortices of reconnection plays also an important role in turbulence. And of course, we are far from understanding these kind of things, I think. And however, one situation when such a collision of vortex filaments can be seen and expected to be derived mathematically is the one that appear in the contrails of an aircraft, right? You have, I put a movie just right after, which will be more clear. But, you have the aircraft, you have the two contrails, and they are initially, there are two straight lines that evolves in time, but that eventually finish in time to cross, to collide. Okay, so the thing will be more clear by sorry. Okay, so this is a movie that Didier Smets gave me. It's a movie made by somebody at an aircraft contest. It is a Hoxie Fury plane. So I'll start the movie, and please don't follow the plane. Follow the pointer. So it is in here. So you see here and here, and then bam. Okay, so things are very clear on this movie. So everybody can see this in nature, and it's a real natural way of seeing crossing of vortex filaments. Now, of course, the problem is that vortex filaments are a very singular configuration in fluids, and we'll study them through approximate model. And there are only, one main model that I have in mind, also a second one that I will talk about a little bit later. And it is due to, well, initially to Zakharov for 2 filaments, and then Klein, Majda and Damodaran did a more complete model that also is valid for several filaments, more than 2. So, what is the model? So, you have, remember, you want to track curves that evolves in R3. So the curve here will be almost parallel to a straight line oriented parallel to the z-axis. So you have a curve like this in R3, a way to parameterize this. So think you place yourself at some height, z. You'll have a location in a plane R2, right, of coordinates x, y, and y, x and y. Well, R2 you can see it as a complex plane. And then at each height, which is a 1D variable, you have a time evolution of a complex number, right? So now the model tells you that this complex function, constructed like this, that fully characterizes the location in R3 of the vortex filament, has to evolve through this 1D Schrödinger system. Okay? So, why this 1D Schrödinger system? So, first, why Schrödinger system? The first part, which is the linear Schrödinger equation, is supposed to model the self-induced motion of one filament onto itself. And why this? Because one has to have also in mind that in the case you have only one filament, you have a model that it is more less, it's still an approximation, but it is more close to the initial problem, which is the local induction approximation or vortex filament equation or binormal flow. Okay, which says to you that if you have one vortex filament, it will evolve in R3 space by simply going into the direction of its binormal with a velocity proportional to the curvature. So you might ask, where is the Schrödinger equation in all this? Well, if you take such a curve of filament evolving through the binormal flow, if you look at its curvature and torsion, it will satisfy a system which is an Euler-Korteweg type of system. And then it was Hashimoto in the 70s that showed that from the curvature and torsion of a solution of the binormal flow, you can construct, in the same way you construct the Madelung transform, you can construct a function, a complex function, that you can check it will satisfy the 1D cubic NLS. Okay, so the motion of one filament is related to the 1D cubic NLS. And in here, actually, when you look at the binormal flow and you take an almost straight filament, putting some oscillation of size epsilon, if you look to the leading term in epsilon, you will end up with a linear Schrödinger equation. Okay, so this explains why in here you have a Schrödinger equation. What about the interaction term? The interaction term, well, is supposed to quantify the influence of other filaments on an initial one, and it is given in the way point vortices in 2D fluid interact one into another. So in particular, if you are looking for solution that, sorry, here it is a zero, that doesn't depend on the height which means you have all same location at each height, which means you have a straight line, right? Well, if you put such a solution in here, you end up that you have to satisfy precisely the point vortex system in 2D fluids. And as an example, you can see through this model the perfect straight line that are supposed to model counter-rotating pair of filaments, the one that appear in the movie I saw you, if everything goes really, if they start really parallel. Okay, so what we shall do is that we'll study a perturbation of such a configuration. So, to say it again, such configuration are, you take R2, you take a configuration of points that will evolve through the 2D point vortex system. And at each location, you put a straight line. This dynamic will give you a solution of this system. And we are looking of small perturbation of this kind of dynamics that will stay close at z goes to plus and minus infinity. Okay, so what can we say about this model to comfort a little bit the fact that it is a reasonable model? Is that it has several conserved quantity. It is an Hamiltonian. And here I put some conserved quantity that will reappear in the following slides. And in blue, you have the quantities that are, that are conserved by the 2D point vortex system. Okay, so before going forward with the analysis of vortex filaments, the next slide will be to recall some known facts about 2D point vortices, as will work near configuration that are locating perfectly into the point vortex location. Okay, so for instance, if the circulations gamma are all positive, then you don't have collisions. Collisions means that in finite time, the points of the filaments touch. For the filament, if it happens at one height, that you have psi j equals psi j prime. Okay, so if all circulations are positive, and you imagine that you have some points xj that will get very close to some point xk, from this conservation of energy, you will need also to compensate, you will need also to have another pair of points that will get very far one from each other, right? Because when you have two that are getting very close, the logarithm goes to minus infinity. So if you want to have conservation and all the circulation are positive, you need to also have some logarithm that will go to plus infinity. So you need to have a pair of points that get very far one from each other, and this will contradict the separation momentum conservation. So first result is that if you have a positive circulation, you have global existence for the point vortex system. Also for the separation momentum conservation, you obtain that if you have only two point vortex, then they will stay at the same distance, and they will rotate or translate in the case of opposite circulation, which are called counter-rotating point vortices. Okay, so what's happening? As you can imagine, more point vortices you put, things get more and more complicated. So for n equals 3, already you have explicit collapse configuration. This was proved by RF, what you do is that you write the point vortex system in terms of the distances between the point vortices. And then you get a configuration which is in the shape of triangle that turns and shrink at the same time, and eventually everything collapses to one point. Okay, some very important configuration are the one where you place vortex points in the vertices of a regular polygon of same circulation, and the configuration rotates with an angular velocity that depends on the number of points you put, and also on the circulation and on the radius of the regular polygon. Also, you can place also, as before, vortices in the vertices of the polygon and put one in the middle with another circulation, not necessarily precisely the one you put on the vertices of the polygon, and you get a configuration that rotates with a speed which is given by a combination. And here we can note that we can choose a gamma 0 in the center such that the configuration doesn't move. Okay, and then things are really getting richer and richer, and for instance, to give you an example, it was Kelvin's conjecture that the polygon configuration is stable up to 7 points, and this was finally solved in 2002 by Kurakin and Judovic. And for this I can cite Aref's review and also Campbell-Ziff catalog of 2D vortices for other configuration of 2D vortex point on concept, on circles or other things like this. Okay, so now back to the initial problem of filaments of vorticity. I will spend most of my time actually on recalling what it is known for the system I presented on the first slide. And eventually I'll want also to collision in the case of two vortex filaments. So initial results come with the ones that derive the model, of course, and they prove in particular that for n equals 2, for circulation of same size, same sign, the system is, the linear system is stable, and they give numerical evidence that suggests that global existence should hold for same circulation, and collapse should occur for opposite circulation. Okay, also Lyons and Majda worked on this model, and they construct some global but very weak solution, which means you don't detect any more collisions. And then, as you can imagine, people from dispersive community get knowledge of this very nice model and try to do things. So Koenig, Ponce, Vega put themselves in the classical situation where you count the perturbation in H1 under smallness condition, and they prove local existence. And also they prove global existence for some configuration that I will explain in one moment after saying precisely how the proof is based. Actually, when the distance between any 2 point vortices of the initial configuration around which you are looking at solution is the same, you can manage to get a conserved energy by taking the Hamiltonian, and I'm sorry, I don't really like doing this, but here, once I do it, here, imagine that these are all the same. Well, you divide the separation momentum by this quantity and you add it in here. Okay? And then you get you get something that it is conserved, and that allows you to prove global existence results. So now the question to understand this condition is very simple. I ask you what are the configuration of points in the plane where distances between any two of them is the same. Well, you can have two, or you can have three at the vertices of an equilateral triangle, and that's all. So this explains their condition. Okay, yeah. Then it is very worth citing these new results. Apparently, it is a fact. This model is driving also concentration in 3D Ginzburg-Landau equation. It's a very recent result of Contreras-Gerard based on a former result of Del Pino-Kowalczyk. And actually, so this is at the stationary level. And actually, Gerard and Smets also announced that they are able to do this in the 3D Gross-Pitaevsky equation. So you have a concentration of vorticity that evolves, concentrated on filament that evolves through the system that we are studying. Okay, so then I recall some results. The first results I got with Evelyn Miot in the next slide. And I should say also, as a final result on this topic, that there are also Garcia Spezia, Craig and Young prove that the existence of time and space periodic solutions around the co-rotating pair of filaments, so with the same circulation. Okay, so the next slide would be the results I got with Evelyn, and there will be, first line will be the results and then some remarks. Okay, so first thing is that, okay, the system is a Schrödinger system, but you put as a condition at infinity that you are close to some constant. So you have to think more in terms of Gross-Pitaevsky setting. And in Gross-Pitaevsky literature, it started in the 2000 that the evolutionary problem was understood better with the work of Gallo, of Gerard, of Gustafsson, Nakanishi, and Tsai. And then the first thing to know is that you have to place yourself in the energy space. So in the energy space, and that's what we have done, so under smallness of the initial energy, you have local existence. That means that your filaments doesn't collide. And one of the interests of putting yourself in small energies is that is a condition weaker than a small H1 norm. And there are some specific solutions that live in the energy space and not in H1. Okay, and now you want to prove global existence. And of course, if you want to prove global existence, you want that energy to conserve energy. And we had the feeling that Koenig-Penzer-Vega argument should be improved in some way. So we did it gradually. So they solved n equals 2 and n equals 3 with an equilateral triangle. So as you can imagine, we start to look around the square, n equals 4 and so the square configuration. And what you realize when you track the energy, I mean, you look at the energy in this context and you want to display conserved quantities and some new quantities that by some miracle would be conserved also. So in this case, precisely, these remaining quantities are conserved if initially you consider perturbations that are of parallelogram shape. So here is exactly what this means. Because if you start with a parallelogram shape at any height, if you look at the equation, you realize that this kind of symmetry is conserved along the time. So then you conserve the energy, and you can get a global result. So then, well, you imagine that you can, what will happen, that you can do it for several, that maybe are some group symmetries that you can preserve, but anyway. So you do some computation, for instance, for n equals 3, or for a hexagon initial configuration, and you realize that your remaining quantities aren't conserved, except if initially you impose very much symmetries, and precisely the same symmetry as the symmetry of the polygon you are working around. So typically here you have a hexagon, and you take hexagon type perturbations. So what this means, if I want to have, if I have first a polygon and at some height, and I want to see a hexagon perturbation of it. What this means? How do you pass from a hexagon to another hexagon centered at the same point? You dilate it, meaning that you multiply by a positive number, and you rotate it, meaning that if you are thinking complex plane, you multiply by a phase. So the answers to put is just multiplication by a complex number different at every height, of course. And the existence, global existence result is that for such a configuration, for any number of filaments located at polygons, then you have global existence. And now this is the beautiful part. If you put such an ansatz, your whole initial system boils down to this single equation, which is a Gross-Pitaevsky type equation. And of course it has a natural energy, and if you compute the energy of the initial system, it will be n times the number of filaments times the energy of your Gross-Pitaevsky equation. So from this kind of equation, we shall get many classes of particular solution, precisely as it was been done for Gross-Pitaevsky. But have in mind, our solution will be something like this, right? So first, traveling waves. So this is some remarks about the proof. They are not difficult. Everything has already been done for Gross-Pitaevsky. You just take them and do the same. Okay, but the main point is that you have existence of traveling waves, which means that at the level of the curves, you have your curves placed in the vertices of a regular polygon, and on each of them you have some distortions traveling in time.
So how many vertices do you have now?
Any. Okay, and then, of course, if you play the trick played by Koenig-Ponce-Vega to use Galilean invariance, then you transform Galilean invariant will multiply by a phase, which means rotation of the filaments at each height. And then you transform your straight line with the perturbation that moving on each straight line, you transform in helices with some small perturbation traveling on it. And this is worth to be said because it is a known work of Hoffinger and Broand that was supposed to comfort Hashimoto's result. That was to say Hashimoto, who made the link between one motion of filaments through the binormal flow and cubic 1D NLS. He took the soliton from 1D NLS and transcribed it in terms of something moving on one filament. And Hoffinger-Broand experimentally displayed such filaments on which some distortion is moving in time, but actually if you go to the paper, they have several filaments which are of helix shape. So this is more related to this eventually. Okay, so now collisions. What happened for collisions, because it was our initial goal, as it was still an open question. Remember, I told you that if you take a regular polygon, you have the choice to put a vortex in the center of a circulation that it is precisely of a size that allows you to say that the angular velocity is 0. The angular velocity appears as a coefficient in the Gross-Pitayevsky equation we have. So when it is 0, you will end up just with the linear Schrödinger equation. And then you can just write a linear Schrödinger evolution that you will control in the sense of saying that it doesn't never vanish at some time, but in finite time it will vanish at some point. Here it is at 0. So you have the picture in here for n equals 3 is that you have one segment, one point in the middle, and you have a straight filament in here and two symmetric filaments that eventually they all three collide in the middle. So now the problem with this result is that you need to have the angular velocity 0, and this means that you have to be allowed to put a vortex in the middle. And if you say in the middle, it means that you have at least two guys.
It's the Gross-Pitayevsky equation, yeah?
For n larger or equals to 2, if you place yourself in this symmetry configuration, then you have only one equation. Phi is the distance from 0. Yeah.
It's only one equation, right? Yes.
Okay, and then you play with this equation and you get several classes of solutions. Okay, so now the issue is that in this case, you have to have n larger than 3. And remember, the plane has only 2 contours, not 3. So what to do? So this is the last part of my talk about collision, really for the initial problem of 2 vortex filaments. But before going to that, I will present also another model of evolution of 2 vortex filament, which is due also to Zakharov. So, but it is in the case where one vortex filament is steady, so located on a straight line, and there is another vortex filament which is supposed to not have any influence on it. So the first one remains straight, and we know how to compute the field around it, or velocity. And then the distance between the small one moving around the straight one is given by this equation. And in this paper, again, explicit helix and soliton type solutions are given explicitly, but only numerical evidence is given for a self-similar collision in the case of opposite circulation. So now we get back to, so summarizing, in the case of n equals 2, as far as I know, even on approximate model, there is no result of colliding for 2 filaments. So we go back to the initial system and we follow the advices given in these papers. So, which is to consider some symmetric configurations. So, if you have symmetric configuration, and of course opposite circulation, your initial system of two equations boils down to this equation. And now what you want is that psi1 vanishes in finite time. Okay, because as they are symmetric, psi1 vanishes in finite time means like psi1 and psi2 get coincide. Okay, so this from the Schrödinger equation type framework is quite an exotic study, because what do you want to find? You want to find an initial data that don't vanish at any point. This is easy, okay, because it's your initial data you prescribe. But you want that to show that in finite time, through a nonlinear evolution, it will vanish at one point. So it is a pointwise control, which is not obvious. It is not a classical thing to do in Schrödinger equation. However, there are two examples of such a thing. One is the work of Merle and Zag about vortex connection with a boundary in another setting. So the first thing they do is the natural one. You change of unknown instead of psi1, you look at the inverse. So when you are looking for things that will that will vanish at one point, means that you'll have some blow up at that point. So you head to what is called a dispersive blow up. In the case of Merle and Zag, it is a dispersive blow up for a nonlinear heat equation, because their model is a heat equation model. So when you do your change, you inverse your unknown, you will end up with a nonlinear heat equation with some gradient extra term, nasty terms. But however, they initially have a blow-up solution, explicit blow-up solution for the heat equation, and they can work around it and construct a solution for their whole equation. While in here, if you play the same trick, you inverse psi1, and then you end up with a Gross-Pitaevsky equation with some extra nasty terms. But already, for the Gross-Pitaevsky equation, you will need a dispersive blow-up data. And this was done recently by Bona, Ponce, So, and Sparber. These are situations that appear and supposed to explain Rho waves. So they are giving initial data that in finite time will blow up in 10 minutes, parfait. Bon, je suis ouais. Non, ça va aller vite. That will blow up in finite time. Okay, so if we take their initial data that will blow up in finite time for the Gross-Pitaevsky equation, the problem is that the regularity of this initial data is too rough to deal with the nasty term we have. So, end of the story, we cannot go in this direction. So, what we do is that we get back to the initial papers, and we look, as advised there, for a self-similar solution that at infinity it goes like two broken lines. And this is what we initially proved with Erwan, Faou, and Miot, that we have rigorously a solution, a self-similar solution for the initial system under the symmetry proposed on the slide before. But of course, now the complaint is that so you have two filaments that will end up colliding, and at collision time you just have two broken lines like this. Okay, the issue is that you are not parallel at z goes to infinity to straight line. Okay, so it doesn't really enter the initial framework in which the system was derived. So what we have done is that we managed to unbend the subsimilar solution, meaning that okay, you have lines like this, but we cut off. We take the subsimilar solution and we cut off in a sense that at z goes to infinity, your approach is precisely your parallel vortex filament you wanted from the beginning, meaning the counter-rotating pair. Okay, so so this is it. You can display rigorously a solution that collide in finite time at one point for the initial system, okay, which roughly at infinity it is two straight lines, and the collision will be in the shape of two broken lines at 0, as expected. Okay, so now just a few words on the proofs. So the first proof is, well, for the subsimilar profile, you have an ODE that you cut in of second order, you cut in two pieces. U is your profile that you can express in terms of V, this V, just by dividing here by x squared and writing U from plus infinity because you want to impose this kind of behavior at infinity. And you remove something here in order to get U far from 0. You don't want the profile to be 0 at any point. Okay, and then you just do a fixed point for the second equation, which involves also U, and you put it in terms of V, in this way. Okay, so you have a fixed point and you do it. And then when you want to unbend this self-similar solution, well, you write the ansatz you are expecting, and you have this reminder term which has to solve a Schrödinger equation with some terms. And then you place yourself in a space where what interests you more is that you can control in L infinity what is happening near 0. And in some sense, you control this little reminder with respect to what is what does the subsimilar solution. And then the fixed point is done by usual use of Strickard's estimates. Okay, thank you for your attention.
Thank you, Valeria, for this nice talk. Are there any questions?
Could you please restore this equation in presence of stationary vortex? This equation, I must say that this equation also has a self-similar solution, which is described. It depends on the sign, of course, because
this is what I told everybody.
Yeah,
that
and it was solved numerically, and we will see formation of gluing of rotating vortex to the center.
I have one remark, and it concerns the following. If you consider just nonlinear Schrödinger with a defocusing case and a psi tends to the constant at the infinity, so you have the usual, Gross-Pitaevsky stationary situation, more or less unstable. And in such a case, it turns out that you can find a soliton solutions in 2D. Yeah. And 2D solutions are very interesting because of a small intensity of, you have a KP soliton lump For larger amplitude, you have a formation of two vortices. And it turns out that if you consider instability, stability problem, it turns out that you have, from one side, you have creep instability for smaller amplitudes and crow instability. And it was demonstrated in our paper with Rasmussen in 1995. Thanks.
Thank you.
Thank you. Any other questions or comments? No. So let's thank Valeria again.